So thank you all for coming. Like Alex said, my name is Maggie Creed. Can everyone hear me okay? Yeah. If you can't hear me, just tell me. So I've been here for 2 years, but I've just started the 4th year of my PhD because I did the first year in the University of Cork in Ireland. And then when my supervisor, Professor Alistair Borthwick, moved to Edinburgh, I had the opportunity to move here with him. So my presentation today is going to be presenting a large part of my PhD work that I've done to date. So looking at modelling water sediment and bed morphological changes. I was going to present something slightly different because in the last few months I've been working on a topic which is quite different really to this, looking at flow through a porous obstacle, which represents a tidal turbine array. But I might present that maybe before I leave sometime in the new year. So for today you just are stuck with sediment. So I'll just give a brief introduction, the background to my work, and then show the mathematical model and some of the results that I've obtained using the numerical model that I've developed. So why, there's a lot of people here probably working with water. I'm not sure how many people are working with sediment. And one of the big questions, I suppose, is why is it important for us to model sediment transport? So firstly, when we talk about sediment, it can range from being very fine particles, so cohesive sediment like clay, and then you can have sand grains, gravel, and even boulders, so particles which are larger than 4 meters, 5 meters in diameter. And one of the things that I've been looking at in my PhD is flood risk modelling floods, dam breaks especially. And what happens when you have a flood is that you have an increase in the velocity of the flow. And so this increase in the velocity causes these sediment particles to be either entrained into suspension and then carried with the flow, or else rolled along the bed, depending on the velocities of the flow and depending on the size of the sediment particles. And in the world, flood flows are one of the largest causes of natural disasters and of fatalities caused by natural disasters. And a recent report from that the European Commission came out with said that flooding causes 5.3 billion worth of damage in Europe alone, and it affects 200,000 people. And that's today, and they predict that with the more extreme events that we're having in the climate, that by 2050 it's going to cost 40 billion euro and it's going to affect over 500,000 people. So just some pictures to kind of show you what I'm talking about. So this is last year in somewhere in Scotland, and this is the river when it's in normal circumstance, and then this is when there was a flood due to increased rainfall. And you can see that the water is definitely not clear. So the brown colour is caused by the presence of sediment particles. And this is something that's around the world. So here is just an image from Sydney in Australia, just a flood that happened earlier this year, or in August actually, not so long ago. And then one of the big problems is these problems of debris flows, so where you have really, really high concentrated flows. And particularly in Asia, so India and in China, they see huge problems with this. So this is was a mudslide that was caused by torrential rain, and you can see that all here is all sediment. So this has been deposited by the flow, and here, so this one you can't really tell what size. You can see that there's some sand, some larger particles, but this can give you an example of what we're dealing with. So these, you can have really fine particles, and this is boulders, like huge boulders that have buried a bus. And these were also carried by this really, well, it's practically just debris. And often after floods, the damage that's left behind is the sediment that's deposited. So the water causes initial damage, but once the water is gone, it's the sediment that needs to be cleaned up. And that's where, especially in terms of economics, that's where one of the real problems is. Just an example of more large particles that can be carried by a flood. So then when the flood dies down, or when the sediment is carried downstream and the velocities reduce, then the particles are deposited onto the bed or into the urban area, depending. And in some, though this can cause damage in like urban flooding, it can also create deltas that then can be used. But in some places, when the riverbed level rises from so much sedimentation, that you have places in Asia again where the bed level of the river, so not just the water level, the bed level of the river is 5 to 10 meters above the level of the city. And then you have the water on top of that. So what happens is that they're constantly having to build higher and higher flood protection systems. And again, the economics of it, and in terms of how long, the durability of it, how long can we keep going, can we keep building these flood protection systems? So this is a lot of the reasons why it's important to model sediment transport. Then one thing that might interest people here in this group, who are, a lot of people are working on offshore renewable energies, so in the north of Scotland, in the Pendant Firth, there's not a huge problem with sediment, but in other areas, sediment can be, there can be a lot of sediment present, even where we want to put, say, tidal turbines. And there was some people here from India a couple of weeks ago, and they were saying that where they are considering tidal turbines, sedimentation is a huge problem. So we need to be able to understand what the impact of these structures that we can put offshore, how they'll affect the flow field, and then how the changes in the flow field will affect the sediment, because not only could it affect the near environment, so just around the surrounding area where the structures are placed, but in the long term it could also affect the coastal area. So this is a huge problem of all these different scales. And then in terms of foundations of offshore structures, if there's a lot of erosion, or if there's a lot of deposition, it can affect the bearing capacity of the structures. And when you're looking at things like offshore pipelines, sediment transport and sediment erosion and deposition can also affect the stability of these structures. So there are many numerical models out there already today that do look at sediment transport. So you might say, what am I doing mine in, and what's different about it? So one of the things is that a lot of the models, some of them are decoupled, so they update the hydrodynamics, and then they take it that the bed changes happen at a slower rate, so they decouple the problem. And other models either look at just bedload transport, so when the particles are large or when the flows are less intense, or they look at just suspended sediment transport, so this is when the particles are entrained into suspension. So one of the things that I wanted to do with my PhD was to see if it's possible to develop a model that is fully coupled, so at each time step the hydrodynamics of the flow is updated, and at the same time the sediment concentrations are updated and the changes in the bed are updated, so in every time step. And I wanted to include bedload transport and suspended sediment transport and see what happens if we can have the two of them in together. So also one of the things is that I'll show the equations next, but they're quite complex, and often the equations are manipulated, and some of the terms, the conserved variables, are put in the source terms, which makes the source terms more complex, and it kind of increases the complexity of the numerical model and the methods needed to solve the problem. So I have developed my model from scratch, so using Fortran, and the first thing to do was to derive the equations that I was going to use. So I call them the shallow water sediment equations. If you're not familiar with shallow water, it's when we assume that there's no change in the vertical acceleration, so that we have this, it's a depth averaged flow, and it's when the horizontal length scale is much bigger than the vertical length scale. It has its limitations, but for this problem, it's the one I chose to look at. So you just take a piece of the flow and the bed and divide it into three areas. So here are two main areas. Here is where you have the water-sediment mixture, so either it can be clear water if there's no sediment present, but also if there's sediment present, then the density is no longer the same. And then you have the bed, and kind of do a look at the mass conservation of so the mass conservation of water, mass conservation of sediment, and then also the deposition, the net deposition or entrainment of sediment, like the interaction between the water column and the bed. And we come up with these equations. So if you're not looking at any mathematics and you hate equations, don't worry about them. But if you are, they're a little bit different to some of the standard conventional shallow water equations that you know. Often this term, the rho, is not present in the shallow water equations because the density is constant. So when you have clear water, you remove the rho term. And in most numerical models that look at coupled modeling, they also take this density term and they place it in the source term. So this is where I wanted to try and retain this structure of the equations and see if it's possible to solve them. And then in the source terms, especially, so like in the first equation, so the mass conservation of the water-sediment mixture, those source terms are related to the changes in the bed. And then you have these two parameters, D and E. So D is the deposition, the rate of deposition, and E is the rate of entrainment. And both of them are calculated using empirical formulae, which I know some people don't like very much, but it's what I've been doing for my model. And then these terms QB, X and QBY, it's the rate of transport of bedload. So in order to facilitate the solving of the numerical model, I've replaced the dependent variables with 4 new variables, and then I've updated these variables at each time step, and then just using substitution I can find the values of the standard primitive variables that we find in the shallow water equations. Yeah, I've used a good enough type finite volume, so it's a finite volume scheme, and I've used Mussel-Hancock time integration, so it's second order in time and in space. And then for the bed equation, which is not a standard advection equation like the other equations, I've used finite differences, so a combination of second order central and upwinding. So some of the more interesting things, some of the results that I've obtained. So I'm just going to present 2 of the cases that I've looked at, and both of them are dam breaks. So one of them is a simple, well not simple, but more simple dam break. It's it's a uniform dam break, so the entire dam across the width of the channel is removed at the same time, so it's a little bit like a 1D dam break, and the entire bed is erodible. So, and in terms of scale, this is a 50-kilometer long river channel, and the upstream depth is 40 meters and the downstream depth is 2 meters, and the particle size is 4 millimeters that I've been looking at. So these are just some of the results that I've obtained. So these are XT plots. So this is X, and then this is in time. I've just so you can see how each of the components varies in time. So the free surface elevation, so it's like the depth of the water, and the concentration of suspended sediment, the velocity of the flow, and also the update of the bed level. And what you can see here very clearly is, maybe I should use this. I'm not really good at these. So you can see that this is the celerity of the wave as it propagates downstream. So after the dam is removed at this time here, and you can see it begins to propagate downstream. And immediately, because the velocities are quite high along this front, you begin to get erosion. So the bed begins to erode, and at the same time the concentration of suspended sediment increases. So instantaneously when the dam breaks, because the velocities are so high, that you start to get this entrainment of sediment. And you can see that the sediment that's in suspension is carried downstream at the same speed as the water particles. And also here, so normally if you have a dam break over a fixed bed, you don't have this second front. And the reason that this is developed here is because you can see that the concentration of suspended sediment falls abruptly. So in order to have mass conservation, then you have this increase in water depth. So these are the results that comparing them to other numerical models. So the blue line is when I have suspended sediment only. So in the red, this is results that were presented in the literature, and they assumed that there was only suspended sediment, so they assumed that there was no bed load. Because of this type of a dam break, the velocities are so high that you wouldn't have a lot of bed load transport. But to check what happens if I do include bed load, I did a couple of other tests. So the one in the black dotted line, which is very similar to the blue line, so the blue line for me is a case where there's no bed load, and the black dotted line is a case where I have allowed for bedload, but I've used a condition called the Rouse number, which determines, depending on the shear stresses, the shear velocity, and the settling velocity of the sediment particles, it determines whether you have suspended sediment or bedload transport. And so because there are some slight differences, but it's pretty much the same because the case is predominantly suspended sediment transport. And then to see what happens if I don't use the Rouse number, I did this case 3, which is in grey, and you can see that because I have included bedload, even though like I've added bedload, even though in the situation it might not be, you wouldn't expect bedload, that it does actually change slightly the final formation of the scour hole and the final free surface elevation profiles. So then I'll present this kind of more interesting one. And this is a much more complex case because, so firstly, it's a partial dam break. So there's only, the dam is only broken here. And the bed is only partially erodible. So it's erodible over this length, and then you have this non-erodible bed. And the channel is also it's quite narrow. So I'm going to show some videos. See. So this first one is the free surface elevation. And you can see that, so this is, as the flow leaves the dam breach like a very fast jet, and then it kind of spreads out and begins to propagate downstream. But just in this area where you have the erodible bed, you have these almost like solitary waves or standing waves which develop. I'll just go to show the bed load. This is the bed, or the bed elevation. So you can see immediately that there's a scour hole is developed just downstream of the dam where the water is coming out, and the velocities are so high that the scour hole is much deeper just downstream of the dam where the flow meets the bed initially, and then around the dam where you have lower velocities, and you get this deposition of the suspended sediment. And then this is the concentration of suspended sediment. And again, you can see as this scour hole formed, then the sediment is entrained into suspension, and it's carried downstream with the propagating bore front. So one of the things, so these are just some of the results that I have found, and my results are the results in orange. Black is the experiment, and then in the red was presented by Zia et al. 2010. And so there are some discrepancies between my results and the experimental results. But one of the things I didn't mention is that this experiment, there were 6 different sediment size particles, and these results are just for one size particle. So I just chose the median diameter. And also, because it's a shallow water model, I think when you have a scour hole like this that forms so quickly, and you have the water that's coming down almost vertically, that the vertical velocity isn't necessarily negligible, even though I've assumed that it is, because I've assumed it's a shallow water model. So it could be, these discrepancies could be to do with the sediment, which is something that I'm extending to include more sizes of sediment, but it also could be one of the limitations of the shallow water model. And then this is just at a further downstream. I'm just going to show this because it kind of explains some of the phenomenon of these, where you have in the free surface, I don't know, do you remember in the video, there was a lot of these waves, and it looked like maybe it could be numerical error or what's happening. But this is a very simple case. So this is a fixed bed, but you have this flow over a step. And you can see that what happens is when the flow goes over the step, depending on the ratio of the bed depth to the bed elevation to the free surface elevation, and you get these really sharp hydraulic jumps that develop. And this is a simple 1D case. And what happens in the dam break is that you have these hydraulic jumps which develop, but then also at the same time you have reflections from the side walls. So the reflection is reflecting the water into the center. You have these hydraulic jumps that are developing because of the interaction over the bed, and then you get this really complex flow pattern. So I'll just wrap it up. So like I said, I mentioned some of the limitations already. Another thing is that the entrainment and the deposition coefficients are empirical. and there is some uncertainty, as always, with empirical formulae, so they need to be adapted for each case. Also, because the bed and the floor are so coupled, it's necessary to include some kind of smoothing function for the bed elevation, perhaps, and then I'd like to extend this to include non-uniform sediment particles. But some of the advantages is that, so we've shown that it is possible to model the shallow water sediment equations in their fully coupled form without needing to do these manipulations that have been done previously. And it's clear that the interaction between the flow hydrodynamics and the erodible bed is, like, they're completely coupled for these very rapidly changing flows, and so it's necessary to use a fully coupled model. And this can be used to, this kind of a model can be used for flood prediction, especially flood sediment prediction. It's also like a meeting of the east and the west. In the east, we often look at bedload, and in the west, the other way around. In the west, we often look at bedload transport, and in the east, it's suspended sediment transport. So this model has the potential to combine the two, so we can kind of have a broader analysis and a broader comparison between both. And it could be used to analyze the environmental impacts or the effects of offshore and marine renewables. I think I've said some of that already. So thank you very much, and yeah, if there's any questions, yeah.
This production is brought to you by the University of Edinburgh.